Now this is XOR gate properties. Now as per P1 postulate or property P1 we discussed, if one input is made 0, always whatever the other input, that will be receiving in the output of the XOR gate. So this is for, I am keeping two input A as 0, so whatever B it is receiving at the Y. Okay, so I can say A XOR 0 equal to A. Now similarly, if one input is always kept as high or 1, whatever will be the other input, its inverted output will be resulting in the output of the XOR gate. Okay, so I can say A XOR 1 equal to A bar. Okay, so we also already know the equation of XOR gate in terms of AND gate and OR gate is given in the left bottom, A bar B plus A B bar, and circuit is given in 1. That means two inputs A and B, and one input is going along with the inverted of the other input, that is A bar B and A B bar. Again both are ORing and giving the output Y. If you're talking about the NAND gate implementation, we'll be looking like the circuit 2, where two AND gates, two inputs A and B are going to 4 NAND gates, and we'll get corresponding Y. The next slide, we are seeing the left side, we can see 4 inputs A, B, C, D, and T XOR gates. A, B output is going to another XOR gate, and similarly CD output is again going to another XOR gate whose output is Y. So according to postulate 4, we know if any number of inputs are coming to an XOR gate, it can be associatively divided into two input XOR gate. That means A, B, C, D combined together to go into XOR gate can be redistributed to A, B in a single XOR gate and C, D another XOR gate, and both combined by another XOR gate. So this associativity property. Now in this table we can see there are four inputs A, B, C, D, and output is Y. And this table is made to two groups. One group for A is input is always 0. Okay, so we have 8 such cases, and another case is block is right side A, B, C, D, Y with all inputs of A as 1. The main property is we can see that in first row A, B, C, D all are zeros and output is 0. That means number of ones are 0, so 0 is not odd, definitely not even also, but 0 there is no number of ones, so 0 number of ones, so output is 0. Okay, in next input we have D equal to 1, so number of ones in the input is 1. Now it is odd, so output Y equal to 1. Okay, similarly all this first part of the table A has zeros. Okay, and whatever the output Y is depending upon the B and C and D. Okay, so whenever we have odd number of ones in B, C, D, the output Y is 1. Okay, so similarly if we go to table second group of the table, if input of A is kept at high 1, what happens is we are getting X NOR of B, C, D in Y. So the main postulate I can tell is postulate number 3 is if one input is kept high, if A equal to 1, whatever the output is coming at Y will be the X NOR of the remaining inputs, that is B, C, D. So this is actually property 3 we already discussed, and this is very important as we go in design, especially in simplification. Okay, so we have just discussed 4 input to an XOR gate. Next slide. Now this is a simple circuit of a 3 input 3-bit message using odd parity. So first we discuss odd parity. So we can say all the 3 inputs are 0, so odd parity will be 1, and if one input is high, output is 0, the total number of ones are odd. Okay, so in odd parity we have the number of ones should be odd, and the even parity we have number of ones should be even. So here I'll just discuss the odd parity. Okay, next slide we are designing even parity. So even parity means we have to make the all number of ones would be even, including the parity bit. Okay, so you can see the all number of zeros, matlab the first the row will be 0, and last row we can have all number of all inputs are 1 1 1 1. So make it even, we need the parity bit to be 1. Now if we draw the truth table of the circuit in bottom right, we can see there are 8 cells where X is on the row wise and YZ remains the column wise. And if we make 1 all those truth table or cells values, even parity is high, we can get a circuit as top right. Let's go deeper in the circuit. Now this is a Boolean expression coming from the K-map. First is even parity. So what happens is the right side K-map having the values 1, 1, 1 on the diagonal patterns can be simplified using the left part P equal to x bar y bar z, then x y z bar, again x y bar z bar, and finally x y z is in the bottom left of the first K-map. Okay. So if we simplify it, we can say we'll get XORing of the three input XOR get X, XOR Y, XOR Z. So that is for even parity. Now let's see for odd parity. We have the K-map on the bottom right. So if we formulate the expression using the bottom K-map, we will get the expression X bar XOR Y XOR Z. Now we can see the difference is X having a difference between the even pair expression and odd pair expression is the X have a negation. Yeah, that's it. So this is according to property I think property 3. Yes, if we want XORing of the other inputs, what is the result? We just need to make one input as negated. Okay, here we need the XNOR of the Y and Z. So what we'll do, we just invert the X bar. So this is difference between the expression of even pair and odd pair. Now this is the circuit. The parity generation circuit. What we'll do, all the message signals are passing towards an XOR gate. You can see X8 is the output of the XOR gate, and combined they become an even parity. Okay. Similarly, for odd parity case, all the inputs are going to a XOR gate plus a NOT gate, or in general it's an XNOR gate. So what happens? The output of the XOR gate will be 0, 1 for even odd number of ones, then that will be converted again to 0. So net the number of ones will be odd. So this is a circuit of odd parity in the middle. Okay. The data or information we have no control, it will be random. So based on the random data coming as input, this XOR gate generate even or odd parity, it will send to the receiver. Now let's see the receiver circuit. Now in receiving, what we have is all the received signals are inputs or bits are going to a XOR gate in case of odd parity. Okay, so if odd parity, we assume that the number of ones coming is odd. So if all those are going to XOR gate, the output of the XOR gate should be 1. That means it is still maintaining the odd parity. So the odd parity is 1. That means we can accept the message because it is the system we are designed is odd parity. That means it is right. For example, but in the other case, if you have even parity, what happens? All the ones should be, number of ones should be even. That means XOR output should be 0. Okay, so that we need to a NOT gate to make it 1. So that even parity output is XNORing of the inputs, and the output is 1. That means it is maintaining the even parity. That's the simple logic, and that's it. As the number of inputs increases, we just need to give all those into an XOR gate for even parity checking and XNOR gate for odd parity checking. Sorry, reverse. XOR gate for odd parity checking and XNOR gate for even parity checking. Okay, that's it. Now this is simple two-dimensional parity check. Now what is here is the original data message is given with 8 bits into 4 blocks. That means 8 into 4, 32 bits are going as input. Now what we'll do is we divide the 32 bits into 8 bits and keep it in row wise. Now we generate a row parity and a column parity. So row parities, as you can see in the right side, and column parities is you can see in the bottom side. Okay. Now what is the function of this bits? Let's see. Now here there are 32 bits as the sending. So all the row wise, what they will do based on the even parity check, you can see there in first row we have only 4 ones, so row parity is 0 if you are following even parity. Okay, and second row we have 4 ones, and so we have the row parity 0. Again we have 2 ones in the third row, again we have so parity bit 0. Okay, and similarly 2 in the fourth also, so we have row parity 0 there also. Now coming to first column, we have 1 1 1 3 ones in the first column, so to make it even we need 1, and so on and so forth. Now we got row parities and column parities, and one more bit we'll discuss in next slide. So what we'll do, while transmitting, we transmit this row in a single block of 9 bits. Okay, so we can see the first row including the row parity, we make a package and we put in the first data block, and second row including the row parity will make second block, and so on and so forth. We have now 1 2 3 4 5 blocks. So if 5 blocks, we have 9 bits, so total 45 bits. So initially we have 32 bits. Now after including the parity bits, we have 45 bits. Okay, now this slide shows the a bit more detail, like how the two-dimensional parity is working. So we know the message signal is outlined in blue color, and the parity bits, row and column parities are written in red color. Now what about the one which is in the diagonally placed along the message? Now the function of that one is it directly gives the parity of the whole message signal irrespective of row and column. It just counts the total number of ones in the whole message, and if it is odd, that is made 1. If it is even, that is made 0, provided we are following even parity. Okay. Now in this slides, what happens when one bit is corrupted? Now if the receiver receives some information, and if one of the bit is changed, say for example in the left picture, the one bit is changed, what happens? The bottom, which is column parity, is changed, and corresponding row is also changed. So we know that whenever one bit is changed or one if it is corrupted, we have two parities are changed. One is row as well as column. Yeah, the diagonal bit also will be changed. Now the second, in the right figure, here there are two bits are affected. So when two bits are affected, we know both are happening in the same column, sorry, same row. So this row parity will not be affected, but both different column parities will be affected. So we can say two bits are changing in the same row, no row bit will be affected because even number of still maintained, ones are still maintained. Okay, and column bits will be changed. Okay, now here we can see there are 3 bits are changed. We know that in the 3 bits, 2 bits are in the same column, so that column parity is not changed, and only one column parity is changed, and the 3 row parities are changed. So here we can see there are 3 change in corrupted bits makes change in 3 rows and 1 column parity. Now in the right side we can see the special case 4 bits are changed, and 2 in one row, 2 in another row, and 2 in one column, 2 in another row. So no, in net effect no parity bits are changed. That means even though there are 4 bits are corrupted, 4 bits are changed, still the receiver receives no change in the parity bits, and it will accept the message, the correct message as such, and it cannot distinguish between the right and wrong provided this kind of situation arises. Okay. Yeah, the solution is, you can see given, so all whatever you want to, if even parity you want to make the even number of ones, odd parity you want to make the odd number of ones. Okay, just need to count and make it even, then even parity or odd parity. So it's a memory based question. On question 1, you're given a full set of A, B, C, D, and you have to, it's assumed that it's even parity, the system is an even parity, you have to find which receive. So this is received by the receiver, so you have to find which among this A, B, C, D the receiver will generate an error. So pause the video, you try to find the answer. The answer is C. Okay, so what we have to do is just to write the data and parity bits in order and check whether there is even number of ones. If there are even number of ones, there is no parity error, but if there is no even number of error, that means odd number error, there will be error. So that case I'm received case C. That means there are only 3 ones, so there is no even parity maintained, so there is a parity error, so the receiver has to discard the data. Yeah, we have given a 4 points, 1 2 3 4. You have to pause the video and find the correct answer. This topic, these are my references, and